The projection. The projection is the next point after rotation. Projection means, as we have seen that rotation, projection, reflections and all, the briefly goes to the lower dimension as we saw. Now let's see what is the projection of a theta line. So on a theta line we are going to see what is the projection. So during this, as let's consider the projection of 1 0 and 0 1, and we'll have a theta line. This theta line, we know that if a line is drawn, let's consider this as x and y axis, and we were representing like this 1 0. This 1 0 is having its length as this much, and when this vector is rotated, then certainly it's going to be in this fashion. By an angle theta, if we rotate, it goes in this way. Now its length, its value will not be, its length is 1, but its points are what? When this vector is rotated, certainly it's going to be like its x vector and its y1. So when it is rotated on the y-axis, it will go to this place. So it would be 0 1. But when it is there at a theta angle, when it is making an angle theta with the x-axis, then it can be resolved into two components, and this would be our cos theta and sin theta. So we were writing this point as yes, C and yes. Now we want to go for the projection. What exactly is the projection? The projection of 1 0, let's draw it. The projection of 1 0 means drawing a line so that it will be perpendicular to this vector. Drawing a line from 1 0. Then if I draw a line, of course if this has to be perpendicular, then in this way we need to draw the line. Let's extend in this way. Now certainly as it is perpendicular, it has to be 90 minus theta. So this angle, the length of this side, this length becomes, the value of this length, which is nothing but the projection. And it is clear that when we project this 1 0 onto this line, it is not cutting, or it is not hitting the point, it is not cutting our vector at the point CS. It is bit lesser than that, and the length of this one, as we know it is the opposite side, it has to be, this length has to be sin theta and this has to be cos theta, so this has to be C. Now our actual point will not be C and S. Our actual point is not just CS, it is CS. When 1 0 is projected onto this theta line, it is not just a point C and S, it has to be its length. The length is the scaled version. The projection is scaling this CS by an angle, this point CS by a value C. So it has to be the multiplication by C. So the first vector, the projection vector, the projection matrix, if we are writing, so actually it is CS is our vector, but it gets multiplied with that, so it would be C square and CS. And let's see, what about that 0 1? If it is a 0 1, then the same, what is its length? So let's project it. If we are projecting this 0 1, we need to project, as we are projecting this 0 1, so let's do the projection. When we project it, it will not be again touching, or it is not the point wherein this projection lies on this, or where the projection touches this vector. It is not the point CS, it is something else and lesser than that. And now we know that if what is this angle, so by the theory, if I draw a line, it would be a theta. So in this way it would be 90 minus theta. So the value of this, now this becomes the opposite side, this would be S for that. So this becomes C. So as it is C, the length of, now what is this length? It is S. So our this vector, I mean this length would be this length. Now our CS, we were thinking that the point of projection has to be CS, but this projection is lying, or it is touching at this point. So the length of this vector projected line, the length of this projected vector is of 0 1 is this much. It is only this much. So its value is, this is CS. Of course that point is CS, but it is not the full length CS. It gets multiplied with this S, means only S portion of that will contribute the projection of the 0 1. So it would be S is C and S is square. I hope it's clear. Now let's see what is that. The same is being done here. Now this angle is theta of the line, and when we are projecting this 1 0, its value would be S. So C is scaling that point CS, because the projection will not be just a CS, it will be the multiplication by C. And similarly for 0 1 point, it is the S multiplication with that CS. So it is CS is a square. So it is the projection matrix. This projection matrix has no inverse. So the inverse of this one will not exist, because this transformation is not having the inverse. And when these are multiplied, when the P is multiplied with P is multiplied with P, we are getting the P itself, because cos square plus sin square theta is equal to 1. So now this says that the points on the perpendicular line are projected onto the origin. Means this line, if these points were to be projected onto the origin to get the null space, then those would be the same points, those would be the same value. Like the null vector, the null spaces inverse is not existing, because when these lines are being projected, these lines are projected onto the origin, then they represent the same length, so the inverse will not exist. And when we multiply the P square, it would be the P and P with P and P, we get the P itself, because sin square plus cos square is equal to 1. Now the next thing is reflection. As we have understood the reflection, but this reflection is studied with respect to projection here. Just we know the meaning of reflection, the mirror image. So we are learning here with respect to the projection. So let's see this diagram. Here the projection, the reflection diagram is drawn. So for a theta degree inclined line. So here, when we know that this 1 0, if it is projected, it's going to be like C into CS, and when it is projected, when this 1 0 is projected, it's going to be CS into the S. Now the thing says that the reflection of 1 0 is here, as we can see, not necessary that theta line. Now here this theta, the line is drawn with an angle theta. Theta can be anything. If it is 45, then the thing would be different. Now generally we are finding it, let it be theta. Then if this point is there, then sometimes if the theta is something, some other value than 45, then not necessary that it should go at this place itself, because this line is not exactly y is equal to x. So the 1 0, because y is equal to x is one of the condition, so we have to be general here. So theta can be anything. When theta is something else than 45, then 1 0 point may not lie, the reflection of this 1 0 point may not lie at the y-axis, so it may be here. And similarly, when 0 1 point is there, its reflection may lie somewhere else, not on the x-axis. Then in those cases we need to know how the reflection point or how the coordinates of that reflection vector are to be found. So for that, this thing is there. With respect to projection, we are going ahead. So the projection of 1 0 is this. So the thing says that the reflection point is 2 times the projection point. Means the reflection of 1 0 is 2 times the projection point minus a identity vector 1 0. If this is corresponding to 1 0, then 1 0 it would be. And if means its values would be now 2c multiplied with cs, we'll get 2c square and 2cs minus 1, and this is 0. So we get this vector. And similarly, if we are doing it for 0 1, for 0 1 its reflected point is 2 times, because 1 and another 2 times s into c s minus 0 1. So this is the thing. So the criteria here is the projection value, 2 times of the projection value minus the vector. The vector point is nothing but r, 2 times the vector minus the identity matrix, like if it is of whatever the order, so that will be the value. Now for this 0 1, it is 2 times this value minus 0 1 it would be. So in this way, h is nothing but the reflection matrix, which is 2p, p is projection, minus I. So it is 2c square minus 1, as we saw here, 2cs for 1 0, and for 0 1 it is this value minus 0 1, it is 2cs and 2s square minus 1 it is. This reflection matrix, as we have found, so the same thing, by the knowledge of projection we are finding it, and reflections h square, the reflection matrix, like when we multiply the reflection matrices with each other, then if two matrices are multiplied, then we'll get the identity matrix. So this h square is equal to I. Just prove it. H square is nothing but, h is nothing but 2p minus I. When we square it, we'll get this. But we know that projection matrix square is nothing but the same p. And when we write it as p, 4p minus 4p get cancelled. The answer is identity matrix. So this all is regarding the linear transformations. Then the next thing is regarding the orthogonality. So we need to learn the orthogonality. So what is meaning of orthogonal vectors, or what are orthogonal bases, orthonormal unit vectors, and we have to find something like length, and what is the condition for two vectors to be perpendicular, and how to create the perpendicular vectors. We have to go for that. So this here we are going to consider the orthogonality. Then what is orthogonal? Two vectors have to be orthogonal. What is the condition for that? and first we are finding the length of them, and two orthogonal vectors with unit magnitude are referred as orthonormal bases. Orthogonal unit vectors are there. So we'll understand this one when we go for them one by one. So let's see how to find the length of the vector. The length of the vector has to be found. It can be there with the n dimensionals. So let's understand with the 3-dimensional and with the 2-dimensional things. So in those 3-dimensional spaces or 2-dimensional spaces, so we all are familiar with the 2-dimensional thing. What is the condition for orthogonality? What is the condition for orthonormal things? From the knowledge of Pythagoras theorem, we know that if two vectors are there, and to say that they are normal to each other, so there are two vectors, let's say one is x and another is y. The condition for them to be orthogonal is this length is y and this length is x, and let's say z is this length. So x value, this is our x and this is y. So z should be equal to, z square should be equal to x square plus y square. And if the magnitude of these x and y, the magnitude of x and y are equal to the magnitude of z squares. So we know z can be found as square root of that all. If the value of this z square is equal to x square plus y square, then we can say this x and y are normal to each other. And we know that the basics, like even when we draw these axes, it is a 2-dimensional, it is the r square plane, and here the x and y are there, and by default the x and y, of course the axes of our plane, these are normal to each other, the x and y. And similarly, when we go for the 3-dimensional space, in 3-dimensional space also, let's consider this as in 3-dimensional space also, it's our x, y and z, and certainly these all x-axis, y-axis and z-axis, they all are perpendicular to each other. So x is the one which is coming out of this, like we can say it is coming front, but we can't show it on a 2-dimensional plane, so we are showing in this way. And y is the horizontal one and z is vertical, and this one is front, it is coming this way, so it is coming outside of this screen, we can say. Now if we are representing a point, let's say in 2-dimensional, if we are representing a point, let's say the value of this one, if we want to represent a point, then it would be 1, 0. How do we represent? Let's consider this one, it is r1 and 0. And if we are representing this one, it is what? Let's take this point as 0, 2, 0, 2. Then let's say this is our a, or it can be our x, and this can be b, or it is y, and when we join these, so it is nothing but, let's say it is a c. If c square is equal to a square plus b square, then we can say a and b are normal to each other. A and b are normal to each other if a square plus b square is equal to c square. This is 1, 0 and this is 0, 1. That is, what is the c? C is nothing but, it is 1 point minus another, or c is nothing but a square plus, if we know Pythagoras theorem, the reverse way, like c square should be equal to this is 2 square plus 1 square by the Pythagoras theorem. Okay, c square should be equal to a square plus b square. Now here c square should be equal to this, it should be equal to 5. So So it should be equal to 5, the square of this one. So 1 square plus 2 square. Then the values, now this vector 1 0 and the other vector this one, we can draw in this way also and in this way also. So they are normal to each other. Now similarly, if we are representing a point in a three-dimensional representation, in a three-dimensional coordinate system, this is R0, then we need to have, it should be a box or a cube. So let's consider the point as 1 0 0, 1 2 0 and 0 2 0. We know 1 0 0 is on the x-axis, the rest all have to be 0, and this 0 2 0 we have taken. So 0 2 0 2 value we have taken in the y-axis and 3 the value in the z-axis. So individually the points are given in this way. It is a three-dimensional system. Now when we construct a box here imaginarily, now this plane is drawn first by the parallel line, and then these all are being like extended upwards to construct this two. Here the length of the vector, it is not like, it should not be there in a single axis, like it is not the length. So the length has to be there wherein all the three values of our vertices should exist. So when from this origin we extend the line to the front point, we can say the front edge of our box, then now this point is point 1 2 3, because 1, this extension, it is there on the first facet, that is the front facet point. So wherein the x value is 1, y value is 2, from here it is 2 and z is 3. So when from origin this 2 1 2 3 a line is drawn, so to this we say it is our length. In three-dimensional coordinate system, the length is represented, the diagonal as the diagonal. So the diagonal can be anything from here to here, but it has to join the two opposite ends. It has to join two opposite ends. So then it represents the length, and similarly in two-dimensional it would be in this way. So from Pythagoras theorem, we apply the Pythagoras theorem here, like the two vectors are normal to each other if their squares are equal to, if the sum of their squares, like 1 square and 2 square, is equal to 5. And similarly in case of three-dimensional also we'll apply the same thing, like if x1 x2 and x3 are the vertices, let's say x1 x2 and x3 the values, then if that magnitude of x the square should be is equal to x1 square plus x2 square plus x3 square. The same applies to the 4-dimensional, 5-dimensional, like this. So by using this, the Pythagoras theorem is applied for n dimensionals. So when we apply this one, we get the things in this way. So the condition for orthogonal vectors is this one by the Pythagoras theorem. When it has been expanded for n dimensional, then it should be the magnitude of x square plus magnitude of y square should be equal to x minus y, that magnitude square. So here the magnitude of x means it would be the term of x1, x2 and so on. How many are there? What is the dimensional? Those many number of points would come. Similarly y's would come, but on the right hand side we'll get x minus y the whole square. How many number of, like what is the dimension of that? Now this x square plus y square will be equal to x1 minus x minus y the square if. Why? Because when we expand this equation, let's consider this x and y. So let's consider the 2 points x1 y1 and x2 y2. And when we are writing the Pythagoras theorem for this, so it would be the sum, like let's say it is the origin or whatever the point. So with respect to this we are considering, so its values would be x1 square plus y1 square, and these values would be x2 square plus y2 square. So we'll be having those terms, x1 square plus x2 square and y1 square plus y2 square terms are going to be there, because the length of this one, if we are finding the length of this one, it is x2 minus 0, y2 minus 0. Similarly, x1 minus 0, y1 minus 0. So these lengths, so the length of this first and second would be this one, x1 square, y1 square, x2 square, y2 square. This should be equal to what? It should be equal to the length of the C. How the length of the C is to be calculated? By distance formula. Either it has to be x1 minus x2 or x2 minus x1, whatever it may be, but it has to be calculated in that way. Let's find. Now x1 minus x2, so it has to be x1 minus x2 is equal to x1, the length of this one, x1 minus x2 whole square plus y1 minus y2 whole square. Now when we go for expanding this one, so x1 minus x2 whole square is equal to x1 square plus x2 square minus 2x1 x2. Similarly, y1 square y2 square minus 2y1 y2. The same is been explained over here. Like if we consider it as x square plus y square, the length of this is x minus y, means the first point and second point when we are subtracting. So it would be the sum of these x's, y's. It should be equal to x1 minus y1 square plus, in this way. Here we'll have the 2x1 x2 minus 2x1 x2 term, and until and unless that has to be cancelled, this equation will not be true. Like the sum of this x's and y's should be equal to just the sum of the x's and y's. There has to be this term, that is minus 2x1 y1, this all, it has to go 0. So let's consider the points in this way. x1, x2, x3 and so on may be the points in n dimensional, and y1, y2 up till y1 will be the points. Now this x is nothing but the one direction, it is x square, so plus y square is equal to x minus y for a two-dimensional thing. For n dimensional, the values of x's would be n, x1 square, x2 square and so on, and similarly y1 square, y2 square and so on, which is equal to x1 minus y1 the square plus x2 minus y2 square. In this way it continues. That is being given over here. So this will be equal, like x square plus y square will be equal to this value until and unless this minus 2xy is being made 0. When we make this minus 2xy as 0, these would be equal, because the two terms 2x1 y1, x2 y2, these terms are extra in comparison. So for that we go for the condition, like wherein that 2 into xy terms go 0 if the condition that x transpose y is equal to, of course, x1 y1 plus these all terms, this x transpose y is made equal to 0. X transpose y means it can be the x is one point and y is another point. The transpose of 1 multiplied with another point, if it leads to 0, it may be x transpose y or it is y transpose x. If it is giving us the 0 result, then only we can say that the two vectors are normal to each other, otherwise no. So x transpose y means 1, x transpose, the column vector is written as a row vector and this y is as it is. When we multiply these all, we should get a 0, and which all are the vectors. The vectors in whatever the dimension, they satisfy this. They are normal to each other. For example,